Hello everyone. In this video, we are going to cover 6D, statistical inference. What is a statistical inference? Statistical inference refers to the process of selecting and using a sample to draw inference about the population from which the sample is drawn. Okay, it's just a name for that. It's one branch of statistics. The first concept, statistically significant. First concept, statistically significant. So simply put, in my word, what is statistically significant? Statistically significant describes an event or an occurrence or something or a thing. We say something is statistically significant means the thing is rare, R-A-R-E, or the thing happens with a very low probability. Okay, that's my understanding. I hope you can use my understanding to understand this concept. Or if you read the definition on the note, a set of measurements or observations in a statistical study is said to be statistically significant if it is unlikely to have occurred by chance. If you understand that, of course, it's good. But if you don't understand that, an easier way to understand statistically significant means the thing occurs with a very low possibility. We say something statistically significant means the thing is rare, not happen often. Okay? Now here is the thing. If you say something has a low probability or rare, how rare is rare? We need to find a way to measure it, right? So when we say statistically significant, normally we have some condition. We have a criteria. We have a criteria like here. At the 0.05 level, yeah, that's the criteria. Okay, that's the criteria. At the 0.05 level, if we say something is statistically significant, that means the thing occurs with a probability or possibility or chance lower than 5%. Okay, at the 0.05 level, the probability of an observed difference occurring by chance is 1 in 20 or less. 1 in 20, that is 0.05, that is 5%. Okay, of course, we can change the criteria. Depends on how do you decide the criteria. Of course, you won't say 80%. That is not a rare. Okay, 80% is like a majority. Of course, the percentage is going to be low. But how low? Normally, we use 5% or 1%. Those are common used criteria. If we say at the 1% level, something is statistically significant, that means the probability of the thing is less than or equal to 1%. Okay? Yeah, as it wrote here, the probability of an observed difference occurring by chance is 1 in 100 or less. Am I clear about that? In summary, when we say something is statistically significant, that means the thing is rare, R-A-R-E, or the thing occurs with a very low possibility. In order to measure how rare is rare, we have a criteria. Common used criteria is 5% and 1%. If at the 5% level, something is statistically significant, that means the thing has a probability or the chance to occur of the thing is 5% or lower. If we say at the 1% level, something is statistically significant, that means the chance of the thing to occur is 1% or less. Example 1. Are the following events statistically significant? Explain. A. The Major League Baseball team with the worst win-loss record defeats the team with the best record. So you tell me, is that rare or not rare? It could happen by chance or not. I would say if we estimate, that's not very rare. If you watch a lot of games, you might see that's not very rare. So I would say that is that could happen by chance. So it's not significant. It's not something statistically significant. Part B, in terms of the global average temperature, the 12 years from 2001 to 2012 were 12 out of the 14 hottest years on record since 1880. So what do you think about that? The occurrence here, consecutive 12 years out of 14 years are the hottest years. The consecutive 12 years of the 14 hottest years in the record since 1880. I would say that is statistically significant because that is rare. You might feel like, how could that be rare? But if you think the thing, if you put the thing in the history of human being, thousands of history of human being, that is rare. Okay, since 1880, the hottest years, we consider the 14 hottest years, and 12 of them happens between 2001 and 2012. In the bigger picture, it is rare. Example 2. A researcher conducts a double-blind experiment that tests whether a new herbal formula is effective in preventing colds. During a 3-month period, the 100 randomly selected people in a treatment group take the herbal formula, while the 100 randomly selected people in a control group take a placebo. The results show that 30 people in the treatment group get colds compared to 32 people in a control group. Can we conclude that the herbal formula is effective in preventing colds? So what do you think? So let's see the solution. Whether a person gets a cold during any 3-month period depends on many unpredictable factors. Therefore, we should not expect the number of people with colds in any two groups of 100 people to be exactly the same. In this case, the difference between 30% of the treatment group and 32% of the control group getting colds is small enough to be explained by chance. That is, the difference is not statistically significant. And we should not conclude that the treatment made any difference at all. Does that make any sense to you? The treatment group, 30%. Control group, 32%. The difference is very insignificant. All right? is not statistically significant. So next topic, confidence interval estimate. We talked about this concept before, but just touch the surface. Here we're going to go a little bit deeper. How deeper? Here we have a formula for the margin of error. Before we explained the structure of a confidence interval, right? If you recall the previous lesson in the classroom, we talk about the structure of confidence interval. I can say that again here. Confidence interval is an open interval. The center of the confidence interval is the statistic. You know, we only talk about use confidence interval to estimate the population proportion P. So the statistic is going to be the sample proportion P hat. Okay? Population proportion P is just the percentage in the population. And the sample proportion is the percentage in the sample. And if we add margin of error, we have the right endpoint P hat plus E. If we subtract E, the margin of error from P hat, we have the left endpoint of the confidence interval, which is P hat minus E. This open interval with the left endpoint P hat minus E and the right endpoint P hat plus E, that is the confidence interval. We always talk about confidence interval with the confidence level. So here, actually, that is the confidence level, all right? Confidence level and a confidence interval altogether, combined together, make the system for the confidence interval estimation. Confidence level, 95% or 98% or 90%, we require this percentage very high. Confidence level describes how reliable or describes the reliability of the estimation. Of course, we prefer higher confidence level, right? The higher the level is, the more reliable the estimation is. Confidence interval describes the accuracy of the estimation. Of course, we prefer a smaller interval. The smaller the interval is, the more accurate the estimation is. So confidence level and a confidence interval combined together give us the confidence interval estimation system. Okay? Confidence level, reliability. Confidence interval, accuracy. But the two things compromise each other. If we want a very high confidence level, we might have to sacrifice confidence interval to make the interval a little bit bigger. If we want a very small confidence interval, very accurate estimation, then we have to lower the confidence level. Okay? Yeah. If you think about 100% sure, like 100% confidence that the true value of the population proportion fall within tiny interval, that would be too good to be true. So, as I said, the two things compromise each other. We actually talked about those things before. The only new thing here is the formula. We have a formula for compute or approximate the margin of error. It is about equal to 1 over root n. What is n? N is the sample size. Okay? The margin of error for 95% confidence is about equal to 1 over square root of n. N is the sample size. The 95% confidence interval is found by subtracting and adding the margin of error from the sample proportion, p hat, you can be 95% confident that the true population proportion p lies within this interval. The margin of error decreases as the sample size increases. Does that make sense? If sample size is bigger, then the margin of error is smaller. That makes the interval smaller. That makes the estimation more accurate. So that is the confidence interval estimation. Some notations: n sample size or number of trials. I'll explain number of trials, okay? X number of successes. P population proportion. P hat sample proportion. I think I stress the importance of this formula. We have seen this formula before. Sample proportion equals X over N. Yeah, the confidence interval estimation actually is to use p hat to estimate p. To use p hat to estimate p. Okay. Example 3. Suppose the Bureau of Labor Statistics funds 3,420 unemployed people in a sample of n equals 60,000 people. Estimate the population unemployment rate and give a 95% confidence interval. All right. We have this value, which is n, that is given. And what about this value? How do you understand that? That's number of success. You might feel confused. How come unemployment is a success? It's just the name, okay? It's just name. You define what is success. As a researcher, you see randomly selecting a people, randomly find a person has no job. That is a success. Then the number of success is that 3,420. So by using the formula p hat equals x over n, you could find the sample proportion equals 5.7%. You can pause here and use your own calculator to confirm this percent. All right. Then what is the margin of error? What is the margin of error? Remember, we have a formula right now. Margin of error E, capital letter E, equals 1 over square root of n. N is 60,000. You plug in. So the margin of error is 1 over square root of 60,000. Use your calculator. You got the margin of error is about equal to 0.41%. Okay? Center, 5.7%. Margin of error, 0.41%. You add 5.7% and 0.41%. You have the right endpoint of the interval, confidence interval. You subtract 0.41% from 5.7%. You have the left endpoint of the confidence interval. So that is the confidence interval. Is that doable? Yes? Okay. Next concept, next topic, hypothesis testing. In statistics class, we use the whole chapters, actually a few chapters, to really understand what is hypothesis testing. But you know, this course is a big mixture. So we focus on understand the idea. We focus on understanding the idea. So important component of hypothesis testing, that's a system as well, okay? That is a system. Yeah, one important component of the system is the alternative hypothesis and null hypothesis. Null and alternative hypothesis. We use H sub 0 to denote null hypothesis, NULL. We use H sub 0 to represent the null hypothesis. And we use H sub 1 to represent the alternative hypothesis. They are always appear as a pair, PAIR. They always appear together, okay? They always appear together. So we have the null. Suppose we are testing a claim regarding population mean mu, okay? Let's say we are testing a claim about population mean mu. So what does hypothesis testing do? Hypothesis testing is to test a claim regarding a population parameter. So here, let's say population mean, okay? Hypothesis testing is used to test a claim regarding a population parameter. Let's say population mean mu. Yeah, we only consider population mean mu here. So sometimes people claim things, right? You can claim whatever you want. Let's say the claim is about the population mean mu. Then in statistics, we need to figure out a way to test, is the claim true or false? How do we test that? Because the claim is about the population mean, we need to get a sample, right? We need to get a sample. And then we use the sample to set up, we use the sample and a procedure to assess if the claim is true or false. All right? Yeah, the claim true or false, our conclusion about the claim true or false is based on a sample. So one important component of the system is null and alternative. So firstly, you would have a original claim, OC. Okay, OC is original claim. Yeah, this is my procedure. Well, not my procedure. This is the process of hypothesis testing. Always start from original claim. Always start from original claim. The original claim could be written as an expression with mu. Yeah, maybe mu bigger than a number, or mu less than a number, or mu equals a number. Yeah, whatever. Could be an equation or inequality. From the original claim, you set up null and alternative, knowing that the null must contain equal sign, and alternative do not contain equal sign. Actually, in a sense, null and alternative always complement of each other. Okay? We always assume the null is true. Yeah, let me repeat this. We start from original claim and then set up a null and alternative, right? And I always assume the null is true. And then get a sample. And then we consider if the rare event occur in the experiment or not. You know, we assume it's not reasonable the rare event would occur in one trial, right? You know what I'm saying? So let's say, would you be happy someone never buy lottery, but he win today and just buy one lottery and he become a millionaire? Will you be happy, and do you think that's fair? No, because we assume in one trial the rare event not supposed to happen. So we know there's a chance people get a car accident, or there's a chance people get the plane would crash, right? But we know those are rare, R-A-R-E. So if we do not go often, that might not happen. You know what I'm saying? So we assume the rare event does not occur in one trial. We assume, let me write it down. We assume rare event does not happen or occur in one trial. Okay? Yeah, we assume the no is true. We make an assumption, no is true. And then we got a sample. And then we analyze the sample statistic. If we identify a rare event occurs in one trial, that's a contradiction. The contradiction results from the assumption that the no is true. So that means the no is not true. So we reject the no. We support the alternative. If we assume the no is true, and then we got a sample statistics, and then we do not see rare event occur in one trial. We do not have any contradiction. Then the assumption, we cannot reject the assumption, right? So we fail to reject the no. You see what I'm saying? So that's the logic of hypothesis testing. If you repeat this part, what I said should help you to make sense of it. Repeat it, just repeat it. Rejecting the no, we have evidence that supports the alternative. Not rejecting the no, we lack sufficient evidence to support an alternative. Because the no and the alternative are opposite, right? If you are positive about the no, then you are negative about the alternative, vice versa. So let's see this example. Let's see this example. Example 4. A county health official believes that the mean birth weight of male babies at a local hospital is bigger than the national average of 3.39 kilograms. Do you see a claim here? Who claims that? A county health official claims that mean weight of the baby boy, so that's the population mean male, right, is greater than, so bigger than national average 3.39. So did you see the original claim? Remember, the procedure always starts from identify the original claim. Yes, original claim here is male, population mean male, bigger than 3.39. The population here are the weights of all the baby boys in accounting. By the way, in accounting, okay? Yeah. The person claims male is bigger than 3.39. And then we are going to go ahead to find the no and the alternative. The no is always male equals the value. And the alternative is the same with original claim. Okay? Yeah, alternative. If the original claim does not contain equal sign, then the alternative is always equal to the original claim. Let me say it again. That's a rule. If the original claim does not contain equal sign, then the alternative always equals the original claim. The no is always equal. All right? So we have original claim, we have a no, and we have alternative. Now we assume the no is correct, okay? And then we got a sample. Let's keep reading here. So a random sample of 145 baby boys born at that hospital has a mean weight of 3.61 kilograms. Assuming that the mean birth weight of all male babies at the hospital is the national average. Yeah, so we assume the no is true, right? So now we got a sample. The sample size, let me write it down. Sample size n equals 145. And the sample mean is 3.61. Okay? Yeah, that 154 baby boys from the hospital has a mean weight 3.61. So that actually tells us the sample mean. Sample mean is the sample statistic. We use the sample statistic to estimate the population mean. We use the sample mean to estimate the population mean. So here, so the sample mean is 3.61. Let's keep reading. A calculation shows that the possibility or probability of selecting a sample with the mean weight at least 3.61 is 0.032. 0.032. And is true or is high or low. So now we got a sample, we get a sample mean. And we figure out the probability that the sample mean is at least 3.81. The chance is 3.2%. You know, here we need to have a significance level. Significance level. Alpha. We use alpha to represent the significance level. Significance level alpha is another important component in the system. It's always given up front. So if we say alpha equals 1%, how about that? If we say significance level is alpha is 1%, means if the probability of the event is equal or less than 1%, that is statistically significant. That is rare. Remember rare, R-A-R-E. So now 3.2% is bigger than that, right? So it means it's not a rare. It's not a rare. It's not a rare, that means we have no contradiction. Means we have no reason to reject the no. Okay? In that case, we are going to fail to reject the no. Fail to reject the no. Fail to reject no kind of like a support no, right? And we deny, kind of like a deny or lack of confidence evidence to support the alternative and the original claim. But what if alpha here is 5%? 5%. Then 3.2% would be rare. That make the sample gives us the rare event. Rare event occurs, then we see a contradiction. The contradiction comes from the assumption that the no is true. So we have to reject the no. We reject the no, then we support the alternative. So we support the original claim. Yeah, repeat this part, okay, over and over. It's not something easy to understand, but it's something interesting and important statistic to understand. So you can see it all depends on the value of alpha package 0.093. I would say this kind of like a beyond the scope. large number law instead. Large number law, LOW. Anyway, so important concept or fact here is sample proportion. Fact here is sample proportion p hat targets population proportion p. So for this problem, take the average of those numbers. Take the average. Yes, this kind of like also related to central limit theorem, but it's beyond the scope. So I'll just tell you what to do. So you take the average of those values. What do you have? If you take those values, take the average of those values. You have what's the mean of this sampling distribution? You will just choose C, okay? Because 14.2%. That's the population proportion. By the central limit theorem, any sample with size 10, those proportion would target those value. Okay, so the average, the mean of those sampling distribution would be P, 14.2%. But you can, how about just ignore this problem because it's out of scope. We use like the whole chapter, like many sessions to cover central limit theorem. And I don't think I have enough time to, in statistics class, I don't think I have time to like explain what's going on in this course. We only have like one session for the whole thing. If you want to ignore, just ignore it, okay? So if you have something in the day quiz you don't understand, email me. I tell you the answer and the period. Number 2, if you take samples of size 16 from a large population, what's the standard deviation of the sampling distribution? This is also beyond the scope. That's B, but let's skip it. Number 3, like it takes a lot of time to explain why the formula is like that. Number 3, suppose you draw a single sample of size 64 from a large population and measure its sample proportion. What's the margin of error for 95% confidence? We can do this one. So for margin of error, that's the formula. N is the sample size. Are we given? Rule 64 is 8, 1 over 8, 0.125. What is that? 0.125, so that is 12.5%. Is that doable? Number 3, very straightforward. Yeah, just ignore 1 and 2. If you have something not that big quiz, email me. People leaving a grocery store over the course of a day, and you find that 12% of those people were overcharged. That's horrible. Find a 95% confidence interval for the actual percentage of shoppers who were overcharged. So we are looking for the confidence interval. All right. In order to find the confidence interval, we need to find the center, the sample proportion, and the margin of error, E. Sample proportion is given. Your sample, which has those 259 people, the sample proportion is 12%. In your sample, 12% people were overcharged, right? And your margin of error by the formula you use your calculator, find the value is 6.2%. And you add them together, you have 18.2%. You subtract 6.2% from 12%. You have 5.8%. So the confidence interval is 5.8% to 18.2%. Okay, so your conclusion would be, I am 95% confident that the true percentage of people go to that grocery store were overcharged is between 5.8% to 18.2%. Does that make sense? Yeah, I am 95% confident that the true percentage of people from that store were overcharged is between 5.8% to 18.2%. So it gives you a ballpark to estimate the true percentage for the population. Number 5, a poll shows the approval rating of a senator to be 45% one day and 42% the next day. Which of the following is most likely the reason for the discrepancy in these sample statistics? A. 3% of the population who approved of the senator at the time of the first poll disapproved at the time of the second poll. B. Between times of the polls, a news story was released alleging that the senator who claims to be for the children is a pedophile. C. The percentage of the population who approves of the senator did not change. The difference in the statistics is due to chance. D. The senator's staff paid the polling organization more for the first poll than for the second poll. I would choose C. Make sense of it, okay? 6. An environmentalist group seeking millions of federal dollars to clean up a polluted lake states in its report to the U.S. Congress that 75% of the fish in the lake have dangerous levels of toxins. The bipartisan committee, like a neutral committee, reviewing the report hires an independent, those are good words, by the way, independent, neutral research group to test this claim in a random sample of 280 fish from the lake. The independent group found 35 fish that contain toxins. Which of the following is most likely true? All right, 35, number of success. Remember, you define what is success. N, 280, sample size. Use the formula P hat equals X over N. Compute the population proportion 12.8%, 12.5%. 12.5% is a lot lower than the claimed proportion, 75%, right? So let's see what happened. The difference in the two statistics is due to chance, and the population parameter is close to 75%, as reported by the environmentalist group. B. The fish with dangerous levels of toxins swim lower than other fish, so they were able to avoid being caught by the independent research group. We do not know that, right? Those details. C. Since cleaning up the lake is a good idea, Congress should have given the group the money without questioning its claims. D. The statistic of 75% reported by the environmentalist group is wrong, and the true population parameter is close to 12.5%. I would support D as in dog, because bipartisan committee independent group, research group, those are positive. And we should trust those the result from them more than the environmentalist. They have a motive to exaggerate the percentage, right? 7. In what circumstance is a result said to have low statistical significance? Means not significant, right? Not statistically significant, not means not rare. Let's see. A. It is very likely to have occurred by chance. B. It is very unlikely to have occurred by chance. C. It supports the alternative hypothesis of an experiment. D. It supports the null hypothesis of an experiment. How do you think about that? Not significant, so not rare. Not rare means have occurred by chance. We should choose A. All right, last 3. The following questions refer to a hypothetical study of 450 people that was designed to determine whether a certain drug was effective in relieving arthritis symptoms. The results are summarized in the following contingency table. Contingency table is a two variable table. It has 2 variables. The first variable, drug or placebo. Second variable, relieved symptoms or not. Those are the table. From the table, we can see that for the treatment group, the success rate is 63.3%. How that? You use 190 over 300. Okay? And the success rate for placebo or control group is 66.7%. You use 100 over 150. Which of the following would be a reasonable alternative hypothesis for this study? We need to identify the original claim first and then set up no an alternative. So what is the original claim? I would say, what's the purpose of the research? You want to see if the drug does better than placebo, right? So I think it would be reasonable to have a original claim. The drug is more effective than the placebo. So this is the original claim. And then the no would be they have the same effect. An alternative would be drug is better than placebo. Again, remember, if the original claim does not contain equal sign, then the original claim is the same with the alternative. I said this, if you repeat the video, you would have heard me say that a few times earlier already. If the original claim does not contain equal sign, if the original claim does not contain equal sign, then the original claim is the same with the alternative. The no always equals. So the no would be the drug was so the alternative would be alternative, which is H sub 1, would be the same with the original claim. The drug was more effective than the placebo. 9. Which of the following would be reasonable? No. The equal, right? The drug was no more effective than. Okay? Yeah, they are complement. They are complement. I know I said it's going to be the same effect, right? But some books, you see that as equal is for convenience. But your understanding of the no would be the opposite or the complement of the alternative. If the alternative is drug does better than placebo, then the complement would be drug does not do better. So the no would be no more effective than. The last one, using the percentage of drug-taking patients and the placebo of symptoms, how do the actual results compare to the results expected according to the alternative hypothesis or the null hypothesis? So we'll see the two groups really have a similar success rate. Actually, placebo group has a higher success rate, right? So what do you think? The results agree with the no only. What's the no? No is the drug was no more effective than the placebo. Yeah, try to make sense of it. All right, that's everything about this section. It's not very straightforward. It takes a lot of understanding. So I recommend repeat the video. Repeat the video, okay? If you have any questions, please email me. Thank you for watching.